in the previous class we had discussed about successive approximate ATD converter. Before that we had discussed dual slope ATD converter and its applications. So, we had shown also how to apply the ATD converter with respect to solar cell. So, today we discuss about first DTA converter and then we again get back to other ATD converters. So, we discuss about DTA converter, digital to analog converter. Digital, so we call DAC. There are two types of digital to analog converter, that is when a digital word is given and we want equivalent analog output. So, general block diagram would be that we have a digital input are given, for example, 4-bit converter, we have LSB here, MSB here, that the input zeros and ones, and DTA converter, and this has a reference voltage V reference, and then we get analog output V output analog. So, this is a general block diagram for DTA converter. So, essentially that analog voltage analog output actually nothing but V reference voltage into digital word actually. So, we for example, we have all bits are 1, in this case it is a 4-bit converter. So, we have number of bits high, that is a binary value divided by 2 power n. For example, if it is a 4-bit converter, then it is a 1 volt V reference equal to say 1 volt and n is equal to 4-bit converter. Then analog output V 0 would be equal to 1 volt into 2 power 4, that is actually into binary value. So, that will be 1 by 16 into, for example, if one LSP alone on, say if we have a logic 0 0 0 1 for this, then the binary value is 1, then you have 1 by 16th of a volt. Similarly, for example, if all bits are high for 1 1 1 1, then V 0 would be this is for this actually. So, then V 0 would be 1 volt divided by 16 into 1 by 15. So, 15 by 16 volt will be the output. So, this is what the DTA converter is doing. So, we will have again the output voltage depends upon the V reference and then the number of bits that we are using for digital input. Now, having seen the general working of DTA converter, let us see now the types involved and then closely see how they are working. There are two types of DTA converter, two types of DTA converter. One is actually binary weighted DAC. The second one is R2R network based DAC. There are two types of DACs are available. Now, we see first one, so binary based. So, the first binary based DAC, binary weighted DAC. Now, in this case what actually done is we have a resistance and then assume that we have a switch here, that switch actually can connect either to this or to this is connected to ground, then or it can connect to this one. Same way we can have for example, I take 4-bit converter. So, in the 4-bit DTA we have example 3-bit, then 4th bit I put it here. So, assume this is a digital word that is operating the switch, it also can go to ground. So, you have MSB here, least significant bit is here. Now, this output, for example, I connect to the op amp, then I put a resistance here and that act as a output. This resistance what we do is we take R, then 2R, 4R, 8R. So, now these resistors are actually now binary weighted. For example, if this 1K, I make this one 2K and this is 4K and then this one 8K, and this resistance can be any amount, there is no problem. This is Rx. So, what happens is when MSP is high, when MSP is 1 and all others are 0, it's 0. That is, we have a condition for 1 0 0 0 input is 1 0 0 0, then we call that is S1, S2, S3, S4, then S1 on, then S2, S3, S4 off. Then this actually given to V reference, is given to V reference, then S1 on, S1 this is off position, on position, connected to op amp, this all connected to ground, all connected to ground. Connected to ground. Then current to the minus input, then current I to the inverting terminal, inverting input of op amp is V reference by R plus 0, second stage, third stage 0, third stage 0, because other currents are actually connected to ground. Similarly, we can also show that if for 1 for digital input, for digital input, for digital input 1, then I would be VR by R plus VR by 2R plus VR by 4R plus VR by 8R. So, like that we can have, depending upon the digital input, whichever digital input is high, then you will have the current output. Then the final output voltage at the output of the op amp, because we have used the summing amplifier, op-amp is summing amplifier. So, all the current whatever is coming is actually passed through the resistance R x. So, you have I here coming here, that is the output voltage, that is equal to R x into I with the minus input. So, the depending upon the digital value you will have a analog output. This is a general purpose binary weighted A to D converter, DTA converter. However, this converter has a problem in the sense that we have to have 4 accurately calibrated resistors are required. For example, if I have 1 k, then 2 k, 4 k, 8 k, and each resistor should be accurate to 2 power 4. In this case, that is 1 in 16 accuracy is demanded. Suppose if I go for 8-bit converter, then for 8-bit converter, we need 8 resistors, that is we need actually the same we need the same 8 resistors. If you look at these 8 resistors, the accuracy demanded automatically goes high because we connect we connect join all of them. We join all of them and then so we will have, for example, 1 k, 2 k, 4 k, that will be 8 k, 16 k, 32 k, 64 k, 128 k, and then this is the output current, that is a digital word switching each one separately. Now, the problem here is that I had to have, if I take this accuracy requirement, I need it is a 2 power 8, that is 1 in 256, 1 in 2 power 8 accuracy required for all the 8 resistors, 8 resistors. So, that will amount to getting that includes temperature trip. Against the temperature also the accuracy should be maintained. That is quite difficult. For example, in quickly even for 8-bit converter we need 0.4% accuracy resistors against temperature, against manufacturing tolerance. So, that is a difficult thing to get, particularly for example, if I go for 16-bit converter, then accuracy goes 1 in 2 power 16, and that is definitely not achievable with the production constraints that we have. So, this binary weighted R to DTA converter is not very popular because of this reason. So, the other ATD converter is actually R to R network. So, in binary weighted resistors, resistor based DAC, accuracy requirement for resistors this is a difficult to achieve. Particularly for high bit DACs. So, this is the main drawback of this. So, that is why we have R to R network based DTA converters. So, we see how the R to R network based DTA converters are working. So, we will take R to R network based. based DAC. So, to avoid so many resistors, to avoid putting so many resistors of required accuracy, we can have only 2 resistors fabricated in R2R network with the required accuracy, and one can easily achieve the required function with the lower cost. That is R2R network is very popular, and in fact, most of the converters are actually R2R network based DTA converters only. So, we see how this basic technique works here. In this case, what is done is we can we will understand R2R network first, R2R network. In R2R network, what is done is we can, for example, we can have a R and 2R, and I can have a reference here, V reference. Then I can have another R and then 2R. Then I can have lastly on 2R. For example, here I have R, then 2R and then 2R. Assume that in this network we have here 1 volt. Now, if I have 1 volt at the input, then if I look at the nodes, node 1 and then node 2, then node 3, then node 4. Now, we start from node 4, we take node 4. Now, here what happens, the equivalent resistance of this becomes actually I can draw this. So, you have R 2R, that you have R 2R, that is actually 1, that is 2, then I can have 3. Then the fourth node can be simplified as R and R and R, that is actually the fourth node. Now, if I simplify this, then the next circuit would be I can have a simplified model of this. So, you have R here, 2R, R, 2R. Now, if I simplify this, you can have next that is simplify up to node 3. So, this up to node 4. So, I have simplify up to node 3 now. You have R here, 2R. Then I can make this R 2R. Third one I can show this is R, and then I can write it as R. This is node 3, because if you see this, these two constitute 2R, and that parallel to 2R, that makes it R. So, you have R 2R, this is node 1 and this is node 2, and that becomes a node 3. So, this again is simplified. For example, at node 2 it actually becomes much simpler. So, you have R and 2R, then I have R and again R, that is node 2, that is node 1. Then if I simplify to node 1, then it actually becomes R and R. That is node 1. So, if you carefully see that always we are getting simplified node of R and R. So, if I look at the circuit from 4, then if I look at the voltage at each node, now voltage at node 1 will be if it is 1 volt, that is 0.5 volt, 5 volt, that is V reference by 2. If I look at node 2, then if I this voltage is actually 0.5 and 0.5 again divided by factor of 2. So, this will be voltage at this point will be 0.25 or it is equal to VR by 4, and then similarly node 3 will come as 0.25 VR by 8, and then we will get voltage at node 4 as VR by 16. Now, if you see this is a very interesting property that at any given point, if I see at this point, then the total resistance on to my right and on to my left are equal. If this side, if I see it is having a resistance R, if I see this side, the total resistance will be R. That is true for at any point. If I can see even here voltage, if I look at this point, then effective resistance from this point would be actually R. Then if I look at this point, then you will have R here. So if we keep this one, that is at node 2 you will have effective resistance R, then node 3 also effective resistance R. So that is why we landed up having the binary divided voltage. So without having too many binary weighted resistors, we are able to get binary divided voltage with using only two different resistors R to R. Of course, the accuracy here also to be maintained to the 2 power n bit, but nevertheless we have to fabricate only two different resistors rather than having n different resistors. So one can get a binary weighted voltage using only two different resistors. That is R and 2R. So this is easier to fabricate R only two resistors with high accuracy. That is why this type of converter is very popular. Now let us see how the converter is fabricated using this R to R technique. So here what is done is that you have the resistors R to R is put, then you had the same summing amplifier, we can have this, then we can have the next this is R and then 2R is R, and then we have a next bit can activate this, then third bit, and then the fourth bit. So this is MSB 1, 2, 3, 4 and the last one 2R. So this is 2R and then R and then 2R, R here 2R. Here this is connected to V reference and the output is taken here V0, output is taken from here. Now if you see these are all grounded, so that is S1, I will put it as S1, S2, S3, S4. So the condition would be like this for a digital input of say 1 1 1 for digital input 1 1 1, then condition would be S1, S2, S3, S4 all delivering current to inverting input of op amp, inverting input of op amp. For example, on the other condition if I take for 0 0 0 digital input, that is per digital input 0 0 0, we will have S1, S2, S3, S4 all grounded, that is 0 current to op amp. 0 current to op amp. In between depending on that is whenever it is 1 the delivering current to op amp, if the digital value is 0 it is not, it is delivering the current to ground. So, for digital input of 1 input 1 current is delivered to op amp, current is delivered to op amp by the corresponding resistor, by the corresponding for digital input input 0 current is current from the corresponding resistor is grounded. Since the if you look at the current through the each one, so the voltage this will be VR by 2 and this will be VR by 4 and this is VR by 8 and this is VR by 16 in the case of so the current through this would be when it is on, then the current through this will be VR by 4, then current from here comes VR by 8 because we have VR by 2 here and VR by 4 here, VR by 8 and then this will be VR by 16, this will be VR by 32. So, that way the current is binary weighted and then you will get output voltage corresponding to the digital weight. So, this is the most popular DTA converter because this needs only 2 different resistors which is repeated depending on the requirement of number of bits. Of course, the accuracy maintaining the accuracy in 2 resistors is much more easier, that is why this is popular. So, the normally the practical converters which use this have the following arrangement, that is what they do is they will have these resistors are 2R network resistors, they have a switch here which actually switch this current also taken out. So, we have the other the current is either steered to plus or it is steered to other terminal, one of them, you know, the current flowing through this resistor for example, I can have the current that is coming here can be combined here and then the 4th bit whatever is there, that current also can be added here. For example, this is 2R, 2R, R, 2R, you have R, 2R, then you have here R and then the V reference is connected here and then we have R resistance here, 2R resistance here. So, we have the 2 output currents that is coming here, that one we call I and another one is I bar, because if all of them are 1, I will be for 1 1 1 1, the I would be equal to V by V reference, we take V by 4 plus V by 8 plus V by 16 plus V by 32 and I bar will be equal to 0. For 0 0 0 I would be equal to 0 and then I bar would be equal to V by 4, V by 4 R actually, V by 4 R plus V by 8R plus V by 16R plus V by 32R. So, these two currents can be utilized correspondingly to convert the current into voltage. So, normally what is done is this DTA converters, they show the DTA converter in the following manner. We have the DTA converter and then the two output currents I and I bar are given out. Then the analog input voltage is given to this, and the digital word generally the digital word, actually we can have digital inputs given to this. So, you have MSB and then LSB and DTA converter is coming. If I want the output current, then I can have this, which gives me the voltage, so which is equal to V 0 into I. I can scale the I into R naught, in this case V 0 would be equal to I into R naught. We can also use the minus input, and we can see the various applications how the minus input will be useful. There are applications where we use both plus and minus. There are applications where we use only minus, and invariably plus is utilized. Here the output voltage is actually minus, and it can also be made the A to D converter with the current sinking. That is also another popular A to D converters which is available. So, we will have the another type which is available would be we have a V reference given here, and then we have a digital input. So, you have a DTA converter where the current would be going in I and I bar, and then the output voltage can be obtained now in a positive output voltage will be positive. So, V 0 would be equal to I into R. So, remember if you are using plus, then minus my I bar minus must be grounded. Both I and I bar must see always ground potential. Must see ground potential, then only the converter will work properly. That is why in this case we are used a summing amplifier, and then this I is actually at ground potential, I bar also connected to the ground. So, both the types of DT converters are available, and one can use this, and then R can be suitably selected to scale the output. So, this is how the DTA converter is used, and then there is another DTA converter that we already discussed, that is PWM based DTA converter. This is used extensively in microcontroller applications. For example, if you have a microcontroller, then when the output is connected to PWM, for example, if I have a port P 0.1, then this output can be converted into V 0 by suitably by filtering the pulse width. The pulse width must be proportional to the digital word. Pulse width must be proportional proportional to digital weight. Then the output voltage will truly represent the digital value. However, this has errors because this output 5 volt, the 5 volt may not be exactly 5 volt due to the error in the switches. The output may not be accurate because the supply voltage, because one supply voltage error may not be 5 volt, and the second problem is switches may not be accurate. Switches may not be accurate. There is a voltage drop on the switches. There is voltage drop, voltage loss in the switches. Switches may be considerable. So, because of this may not be accurate. One way of improving this would be you can have switches connected with the PWM output. We have a microcontroller and then plus 5 volt. The PWM output can be suitably scaled using the FET switches at the output. For example, we can have FET switches, and this can be connected to a V reference, which may be say 1 volt, and this can have 5 volt logic. So, the small signal FETs switch on with even 3 volt difference. So, when it is on, this you will have 1 volt, and then this can be filtered with RC, and then we can have another switch here to have connected to another port pin, which has a reverse PWM. That is, when this is 1, this is 0, and vice versa. When this is 1, that is 0, and so on. And this kind of switches will eliminate the problem due to the power supply drift and the on resistance. These switches can be very low on resistance switches, so that there is no error due to the switch, that the resistance R can be selected much larger than on resistance of the switch. On resistance of the switch must be on resistance of the switch must be very small. Compared to R. So, this is an important condition that is required for this to operate properly. So, one can compute the error and then find for 8-bit level of accuracy is more than enough, but nevertheless it is a very slow A to D converter, DTA converter. It is very slow. It is a very slow DAC. That is the main disadvantage of this, because you only have to wait for so much time for averaging to take place. So, the response is very slow. So, some applications where the speed is not a criteria, this is a good choice because it is a very simple. However, it is a very simple DTA converter. It is a very simple, cost effective DAC for microcontroller environment, microcontroller systems. So, we had seen basically 3 different types of DTA converters and how the conversion is done and how one can see the advantage, how one can see the advantage and disadvantage of the converters. Now, let us continue our discussion, that is A to D converter discussion that we had earlier, which we had stopped in the middle to discuss DTA converter, because for A to D converter, as I said, we need DTA converters. Without DTA converters, it is not possible to make A to D converters. At least if you see success approximation A to D and the dual slope A to D converter, they definitely need DTA converters. That is why we have discussed this DTA converters. Now, we will continue our discussion on A to D converters, because there are a few more A to D converters that is to be discussed. So, A to D converters we will discuss now the issues, because earlier we discussed two A to D converters. One is a dual slope ADC or single slope ADC in the microcontroller environment, that also we have discussed. So, generally they are called charge controlled A to D converters or slope A to D converters, or the second type of converter is a successive approximation A to D converters. These two A to D converters we have discussed, and some of the applications also we have discussed. Now, let us see the third type of converter, that is flash ADC. This is another ADC which is very popular, and it is high speed converters, because if you look at dual slope A to D converter, it is very slow, because charging and discharging to take place. Typically dual slope A to D converter, dual slope ADC only 5 to 10 conversions possible per second, 5 to 10 conversions per second. In success approximation ADC conversion time can be roughly 10 to 20 microsecond, because here you need a sample and hold, and that time also to be taken in that. So, this is also not very fast. Nevertheless, 10 to 20 microsecond is good enough for many applications, but there are applications which demand much higher speed. We want to get in a nanosecond level of conversion time, then success approximation ADC is not the correct choice, because success approximation become very slow, because it has to go for 8 trials for 8-bit converters, and also it has to wait for the sample and hold to acquire the required voltage. This problem is not there in the flash ADC converters. In flash ADC, what is done is we will have input voltage connected through a series of network of resistors. So, what is normally done is we have, for example, 4-bit converters. So, we have 8 resistors connected, 1, 2, 3, 4, 5, 6, 7, 8. So, we have there is actually 7 outputs required, 1, 2, 3, 4, 5, 6, 7. Okay, this not the top one I can remove. I can connect this. This is V in. Now, it can be done both way. For example, we can have here R by 2, here or I can have, to make it avoid the fraction, I can have here R here and 2R, and all resistors are 2R. This is not R2R network. and then we will have 3 resistors at the top. So, we will have 1, 2, 3, 4, 5, 6, 7, 8 resistors for 4 bit converters. That is we need actually 3 bit converter. This is 3 bit converter. For 8 resistors need, that is for 3 bit converter, 3 bit converter. That is 2 power 3, that is 8 resistors required. So, the input is divided into 8 different parts using these resistors. Then each one is connected to a comparator. So, you have 7 comparators. So, each one is connected to one input. Say for example, minus, and then we have is connected to minus inputs, then you have a plus input. So, the plus inputs are actually connected to V reference. It can be, there is no reason why the other way it cannot be connected, it can be even connected to plus okay, actually we have to have V input connected to V input connected here, and this is connected to V reference. So, this is a fixed voltage divided. So, we have the V input which to be digitized is connected here, and then the other voltage is connected to each output. So, you have now 7 output voltages, 7 outputs of these comparators. Basically, we have 7 comparators here that actually changes the state according to the input voltage. For example, if the input voltage, if the reference is 1 volt and if the input voltage is 0.5 volt, you will see that the converters, the bottom converters are all, these 4 are on and the top of are off. So, when the input increases by 1 LSB, so we will see that when the input increases, then furthermore the next converter also comes on, then further increase in voltage, the next converter comes on, and so on. Depending upon the input voltage, you will have the outputs of these comparators going high, and this output must be combined in a big logic circuit to be developed, such that you will get the required 3 bit converter out. So, this 8 to 7 to 3 output pin output to be converted and to get a corresponding digital value. Now, essentially what we are doing is we are comparing the voltage to make sure that the corresponding output pins are going high in the comparator. The advantage here is that the conversion time mainly depends upon the response time of the comparators and the conversion time of the logic conversion time. So, the conversion time is very small, that is comparator response time plus logic conversion time. which can be less than a microsecond. There are converters which actually does in a 10 nanosecond time and so on. So, the conversion time is very small and you have the converter output very rapidly coming out. Nevertheless, the disadvantage is, so advantage is very conversion time is less conversion time, disadvantage is large hardware required, particularly 2 to the power of n matched resistors, then 2 to the power n comparators, then huge conversion logic, For example, for 8-bit converter, we need 255 resistors, this is matched, and accuracy of 0.4%, then 256 comparators. This is possible, but so 8-bit converter is possible, one can manage 255 resistors and then 256 comparators. Nevertheless, for 16-bit converter, we need 2 power 16, that is 64,000 resistors, then same amount of comparators, then the huge conversion logic, to convert 64,000 to, that is 2 power 16 to 16-bit output, which is practically impossible. So, there is no 16-bit converter as it is available using the 64,000 register type, but nevertheless we have 8-bit converters straight away available in flash type. So, this 8-bit using 8-bit converters, one can make 16-bit converters with a small workaround technique, because straight away putting 64,000 resistors and converting is almost practically impossible, particularly getting 64,000 resistors, equal resistors, and accuracy of 0.4 divided by 16%, that will come almost 0.001% accuracy resistors required, and that is almost impossible to achieve. So, plus having comparators of that many numbers and their offset voltage, and each one to have accuracy to 2 power 16, if the reference voltage is 1 volt, for example, if it is 1 volt for 1 volt reference, for 1 volt V reference, 2 power 16 converter, the 16-bit converter will give 16-bit converter requires total error of 1 divided by 2 power 16, that roughly works out to be 16 microvolt. This is actually that the 16 microvolt means each resistor should be made such that they divide the 1 volt to the accuracy of 16 microvolt, and also the error in the comparator should be less than 16 microvolt. Actually, if we take half LSP, then the error in the comparator should be less than 8 microvolt. So, both of them are very difficult to achieve, and this also will be very bulky. So, 16-bit converters are not made using this technique. Nevertheless, they also make a 16-bit converter using two 8-bit flash ADC converter. This is called subranging A to D converter. So, that is use two 8-bit flash ADC to get one 16-bit flash ADC. This is called subranging ADC. This is called subranging ADC. Now, this technique is not as costly as straight away making 16-bit converter. So, this is cheaper, that is why the 16-bit flash ADCs use the subranging ADC, or they call pipelined ADC. These ADCs are cheaper and they give 16-bit accuracy at the same time at very high speed. So, you have 16-bit ATD flash ATD converter with the conversion time of fraction of a microsecond, and they maintain the 16-bit accuracy. So, we discuss about the subranging flash ADC converters in the next lecture. Thank you.